In this lesson, we introduce the state space representation, a powerful alternative to transfer functions. We will define the state equation and output equation using matrices. Then, we apply it to two examples, the RLC circuit and the DC motor. So far, we have used transfer functions to describe systems. Transfer functions work well, but they have limitations. They assume zero initial conditions, they only handle single input, single output systems, and they hide internal dynamics. State space fixes all of these. It can handle multiple inputs and outputs, it includes initial conditions, and most importantly, the state vector captures the full internal memory of the system. The linear state space model has two equations. The state equation x dot equals a times x plus b times u plus o times w. Here, x is the state vector, u is the input, and w is the disturbance. The output equation y equals c transpose times x plus d times u. A is the system matrix, b is the input vector, O is the disturbance vector, C transpose is the output vector, and D is the direct feed-through scalar. Let us derive the state space model for the RLC circuit. Recall the RLC differential equation from earlier lessons. This is a second-order system, so we need two state variables. We choose x1 as the inductor current IL and x2 as the capacitor voltage UC. The input U is the source voltage and the output Y is the inductor current, so Y equals x1. Writing the RLC state equations in matrix form, we get the A matrix with entries 0 and minus 1 over L in the first row, 1 over C, and minus 1 over RC in the second row. The input vector B is 1 over L and 0. The output vector C transpose is 1 and 0. And D equals 0. Notice how the A matrix captures the circuit dynamics, inductance and capacitance interact through the off-diagonal terms. Now, let us apply state space to the DC motor from lessons 8 and 9. The motor has two energy storage elements, the armature inductance and the mechanical inertia. So, we choose two states. x1 equals armature current IA and x2 equals angular velocity omega. The input is armature voltage U, the disturbance is load torque TL, and the output is angular velocity, so y equals x minus 2. The DC motor state space model in matrix form. A equals minus RA over LA and minus C phi F over LA in the first row, C phi F over J, and 0 in the second row. The input vector B is 1 over LA and 0. The disturbance vector O is 0 and minus 1 over J. The output is Y equals 0, 1 times the state vector plus 0 times U. This connects directly to the block diagram we built in lesson 9. Each integrator in that diagram corresponds to one state variable. Here is the key insight. Every integrator in a block diagram represents one state variable. For the integrator block, the state equation is simply x dot equals u and y equals x. For the first order lag, x dot equals 1 over t times the quantity ku minus x. For the second order lag, we need two states and two integrators. This means you can read state equations directly from any block diagram by identifying the integrator outputs. To summarize, the state space model uses two matrix equations, x dot equals ax plus bu plus ow and y equals c transpose x plus du. We derive it for the RLC circuit with inductor current and capacitor voltage as states, and for the DC motor with armature current and angular velocity as states. Every integrator in a block diagram corresponds to one state variable. In the next lesson, we will show how to convert state space models back to transfer functions.